Welcome to the Deep Dive. Today we're diving into something truly spectacular, the Aurora Borealis and Aurora Australis. You know those amazing lights you see painting the night sky.
Incredible phenomena.
And maybe you've heard some chatter recently about seeing the northern lights much further south, like maybe even down towards Iowa around April 16th, just this year, 2025.
That's right. Yeah, there was definitely potential for that. It was linked to a couple of pretty significant coronal mass ejections, CMEs, from the sun back on April 12th and 13th.
Okay, CMEs, big bursts of energy from the sun, basically.
Exactly. And the best time they thought people might see something, assuming clear skies, was maybe between 10 p.m. and 2 a.m. local time around the 16th.
Wow. Seeing auroras that far south is usually unheard of, isn't it?
It really is quite something. Usually you need to be way up north.
And this whole thing, this potential southward shift, it's because the sun's been extra active lately, something called the solar maximum.
Precisely. The sun goes through an 11-year cycle, and right now we're in or very near the peak of its activity, the solar maximum.
Okay, so that's our mission for this deep dive then. Let's really get into what causes these beautiful lights, why we might be seeing them more often or further south, and, where you typically have the best chance to witness them. So, first things first. What exactly is an aurora?
Well, the name itself, Aurora, actually comes from Galilei, way back in 1619.
Galileo, wow.
Yeah, he named it after Aurora, the Roman goddess of dawn. He mistakenly thought the lights were sunlight reflecting off the atmosphere.
Ah, a lovely guess, but not quite on the money then. So what's the real story?
The real magic happens when gases high up in Earth's atmosphere interact with something called the solar wind.
Solar wind. Sounds dramatic. What is it?
It's essentially a constant stream of charged particles, mostly electrons and protons, so ions flowing out from the sun all the time.
Okay, so this wind travels across space and hits Earth. Then what?
Well, thankfully, we have a magnetic field. It acts like a shield.
Right, protecting us.
Exactly. It deflects most of this solar wind. But, and this is key, our magnetic field lines also sort of funnel some of these charged particles towards the north and south poles.
Okay, so they get channeled towards the poles by the magnetic field, like a cosmic highway.
Kind of, yeah. And as they get closer, some of these particles get trapped in a layer of the atmosphere called the ionosphere.
The ionosphere, high up there.
Very high. And once they're there, they start colliding with the gas atoms in the atmosphere, primarily oxygen and nitrogen.
Collisions, so they're bumping into oxygen and nitrogen atoms.
Right. And these collisions transfer energy to the gas atoms, putting them into an excited state.
Excited atoms. And that's where the light comes from. They need to release that energy somehow.
Precisely. To get back to their normal state, they release that extra energy in the form of tiny packets of light. Photons.
Photons. So the light we see is literally excited gas atoms releasing energy after being hit by particles from the sun.
That's the essence of it, a massive energy transfer playing out as a light show.
Incredible. Now, we don't just see one color, do we? There are those amazing greens, sometimes reds, even purples. What dictates the color palette?
Good question. It really comes down to two main things. How high up the collision happens, the altitude, and which type of gas atom gets hit. Oxygen or nitrogen.
Altitude and gas type. Got it. So tell me about the red auroras. They seem a bit rarer, maybe.
They often are, and they tend to happen really high up. We're talking above maybe 150 miles or 240 kilometers.
Okay, way up there.
Yeah. And up there, it's mostly oxygen that gets excited. But the air is so thin, collisions are less frequent. So an excited oxygen atom can take nearly 2 minutes to finally release its energy as a red photon.
2 minutes? That's a long time in atomic terms.
It is. And because it takes so long and there aren't many other collisions interfering, the red often appears as these sort of stable, high-altitude sheets or arcs, less dynamic sometimes.
Interesting. So the slowness gives it that look. What about the green, then? That feels like the classic aurora color.
It absolutely is the most common. Green auroras happen a bit lower down in a denser part of the atmosphere, say between 60 and 150 miles, roughly 100 to 240 kilometers.
Okay, denser air.
Right. And here, excited oxygen atoms release their energy much faster. They emit a green photon in less than a second.
Less than a second compared to 2 minutes. That's a huge difference.
It really is. And that speed is why green auroras often have that shimmering, dancing, curtain-like appearance we associate with them. It's much more dynamic.
Okay, that makes sense. Faster release, more flickering. And then sometimes you see purples or pinkish colors lower down.
Yeah, those hues, often kind of a mix of red and blue, tend to show up in the lowest part of the aurora display, below about 60 miles or 100 kilometers.
And what's causing those colors?
That's mostly down to molecular nitrogen. When nitrogen molecules get excited at those lower altitudes, they tend to emit light in the blue and red parts of the spectrum, which our eyes often perceive as purple or pinkish.
So each color is like a little signature telling you what gas is involved and roughly how high up it's happening.
Exactly. It's atmospheric science made visible.
It really is amazing. Now, these light shows are happening here on Earth, but are we special? Do other planets get auroras too?
Oh, absolutely not just us. Auroras have actually been seen on pretty much every other planet in our solar system.
Yeah.
Except maybe Mercury, it's too close to the sun and has almost no atmosphere.
Wow, even on planets like Mars or Venus.
Hmm.
They don't have strong magnetic fields like Earth, do they?
That's a great point. Venus has basically no global magnetic field, and Mars is very weak and patchy. But they still get auroras.
How does that work then, without the magnetic field to funnel the particles?
It's different. On Venus, for example, the solar wind interacts directly with the upper atmosphere itself. It's not guided to the poles. So you can get these more diffuse auroras that might appear across the whole planet sometimes, not concentrated like ours.
Fascinating. So different mechanisms can lead to auroras.
Definitely. And get this, they've even detected an aurora on a rogue planet, a planet just wandering through space on its own, about 20 light years away.
A rogue planet. Seriously. What's powering that? No solar wind out there, presumably.
Right. Scientists think its own powerful magnetic field might be interacting with maybe gas and dust in a disk surrounding it, or perhaps particles from interstellar space. It really pushes the boundaries of where we thought these could happen.
That's incredible. Okay, but bringing it back down to Earth, or at least near Earth, astronauts must get an amazing view.
Oh, absolutely. The view from the International Space Station is apparently breathtaking. They see the auroras from above, these huge ribbons of light stretching over the curve of the Earth. They've captured some stunning photos and videos.
I bet. Gives you a real sense of the scale. So for the rest of us stuck on the ground, where are the best places to go if we want to maximize our chances of seeing an aurora?
Okay, so the prime real estate for aurora viewing is what's called the auroral zone. It's a band around the magnetic poles, generally between about 60 and 75 degrees latitude, both north and south.
60 to 75 degrees latitude. Okay.
And within that zone, there's an even better, narrower band, typically between 65 and 70 degrees latitude. That's really the sweet spot where they occur most frequently in overhead.
Right, so 65 to 70 degrees is the bullseye. Can you give us some actual place names in that zone?
Sure. In the northern hemisphere, places like Fairbanks in Alaska or Tromsø in Norway are right in that prime 65 to 70 degree band.
Hey, classic spots.
Yeah. And the wider 60 to 75 zone includes places like Anchorage, also in Alaska, Yellowknife up in Canada's Northwest Territories, and much of Lapland, which covers northern Sweden and Finland.
Sounds like some potentially cold trips.
Yeah.
What about down south, for listeners in the southern hemisphere?
Good question. The Aurora Australis is best viewed from Antarctica, obviously, but that's not very accessible.
Right.
For more accessible spots, Tasmania and Australia and the southern parts of New Zealand offer the best chances, especially during their autumn and winter months, March to September, roughly when the nights are longest and darkest.
Okay, so latitude is key. But I guess it's not just about being in the right zone, is it? What else do you need?
Absolutely crucial is darkness. You need really dark skies, well away from city lights. Light pollution is a major killer for aurora viewing. Even a bright aurora can be washed out by city glare.
And clear skies, presumably.
Oh, definitely. Clouds are the enemy. You need a clear view of the upper atmosphere where the action is happening.
Makes sense. And just looping back to where we started, that potential for seeing auroras much further south recently, like in Iowa. How many places might have gotten a glimpse during that April 2025 event?
Well, forecasts suggested that because of those strong CMEs, the auroral oval, that's the region where auroras normally happen, could expand significantly. Estimates were that potentially people in as many as 18 U.S. states might have had a chance.
18 states.
Oh, see?
Including places like Cape.
Yeah, stretching from the usual suspects like Alaska and Montana, across the northern tier, through the northern plains, the Great Lakes, down into New England and New York. And yes, potentially even creeping down towards Iowa under the right conditions.
That's amazing. Which brings us to the big question. Why does it feel like we're hearing about auroras more often lately, or seeing them in these unusual places? Is it just that we're paying more attention, or is something actually changing?
It's definitely not just you noticing more. There is a real physical reason. The sun's 11-year cycle that we mentioned earlier.
Right, the solar cycle.
Exactly. The sun's activity, particularly the number of sunspots on its surface, waxes and wanes over roughly 11 years. And right now, as we said, we're in solar maximum.
Solar maximum began around 2019, you said?
The ramp-up started around then, yes. And periods of high sunspot activity correlate very strongly with more frequent and more intense auroras.
Okay, so more spots on the sun equals more light shows here. How does that work? What's the direct link?
Well, more sunspots generally mean the sun is more magnetically active, and that increases the likelihood of big solar eruptions like those CMEs, coronal mass ejections, or strong solar flares.
Okay.
These events throw out huge amounts of energy and particles into space. If Earth happens to be in the path of one of these blasts,
We get a bigger dose of that solar wind.
a much bigger, much more energetic dose. And when all those extra particles slam into our atmosphere, they overload the usual system. They dump energy over a much wider area.
And that pushes the aurora further south.
Exactly. The whole auroral oval expands. Instead of just being a ring around the poles, it swells outwards, making the aurora visible from much lower latitudes than normal.
That explains the sightings in places like Arizona and England back in early 2023 then. Those were due to big solar storms.
Yes, those were perfect examples. Strong solar activity leading directly to auroras being seen way outside their usual zones.
It's incredible. But these powerful solar storms, they're not just about pretty lights, are they? There can be other effects.
That's right. While they create beautiful displays, very strong storms can actually pose risks.
Risks to our technology.
Yeah. The intense geomagnetic disturbances they cause can induce currents in long conductors, like power lines. This can potentially overload transformers and disrupt power grids.
Wow.
They can also interfere with radio communications and affect the accuracy of GPS systems, which rely on signals passing through the ionosphere, the very layer where auroras happen.
So communication and navigation could be impacted.
Potentially, yes. And there's even some ongoing research looking into whether major magnetic storms might disorient animals that navigate using Earth's magnetic field, like whales.
Wheels! That's unexpected. So this beautiful natural phenomenon has a potentially disruptive side.
It does. The sun giveth, and the sun can also, well, disrupteth our technology.
Looking back in history, have there been any truly massive, legendary solar storms that caused auroras on a, almost global scale?
Oh, yes. The benchmark event everyone talks about is the Carrington event. That was back on September 1st, 1859.
1859. What happened?
Well, an astronomer named Richard Carrington observed an incredibly bright solar flare, a huge explosion on the sun. And just about 18 hours later, a massive CME slammed into Earth much faster than usual.
And the result?
The resulting geomagnetic storm was the most intense ever recorded. And the auroras were simply mind-blowing. They were seen as far south as Cuba and Hawaii in the northern hemisphere.
Cuba. That's tropical.
Exactly. And in the southern hemisphere, they were reported down in Santiago, Chile, places where people had literally never seen an aurora before and likely haven't since.
Unbelievable. What must people have thought back then, seeing lights like that in places like the Caribbean?
Reports from the time show a mix of total amazement and, frankly, quite a bit of fear. Without the scientific understanding we have now, many people thought it was something supernatural or even the end of the world.
I can imagine.
Telegraph systems, which were the high-tech of the day, went haywire. Operators got electric shocks, sparks flew from the equipment, and some systems even continued working with the power turned off, running on the current induced by the storm.
Just running on space weather.
Pretty much. One account described the sky looking as if there was a colossal fire on Earth which reflected its flames on the heavens. It must have been deeply unsettling for many.
Wow. What a story. It really puts today's solar activity in perspective. Okay, well, this has been absolutely fascinating. Let's just quickly pull the main threads together for everyone listening.
Okay.
So these incredible auroras, they happen when the solar wind particles from the sun hits gases in our atmosphere.
Check. Interaction with the atmosphere driven by the magnetic field.
Right. And the colors we see, the greens, the reds, the purples, they tell us about which gases are involved, mostly oxygen and nitrogen, and how high up the collisions are happening.
Yep, altitude and gas type are key for the colors.
If you want to see them, your best bet is heading towards the poles, into those auroral zones, especially between 65 and 70 degrees latitude. And crucially, you need dark, clear nights.
Can't emphasize the dark skies enough. Far from city lights.
And the reason we might be hearing more about them or seeing them further south lately, like potentially down near Iowa, it's all down to the sun being in its active phase, the solar maximum, throwing out more energy and particles.
Exactly. Increased solar activity expands the auroral oval. Simple as that, really.
It's an amazing connection between our star and our own planet's atmosphere.
It truly is. And maybe this leaves you with something to think about, considering that Carrington event back in 1859 and how much more reliant we are today on technology that's vulnerable to these big solar storms, power grids, GPS, satellites, communications.
Yeah, that's sobering thought.
Right. So as the sun continues its natural cycles of activity going through these peaks and troughs, what kind of planning or safeguards might we really need to put in place to protect our very technology-dependent world from the potential impacts of the next really big one?
Right.
Something definitely worth pondering.